All right, let's talk about the invisible forces that are, quite literally, running our world right now. I'm talking about electric charges and fields. I mean, they're the reason atoms stick together, the reason lightning exists, and yeah, they're the reason the screen you're looking at right now even works. So let's jump right in and figure out how this all works. Okay, you've totally done this, right? You take a balloon, rub it on your hair, and boom, it just sticks to the wall. Seems like magic, but what's really going on there? Well, it's not magic, it's pure physics. And that little party trick, it's the perfect way to start understanding the fundamental forces that govern, well, everything. We're going to break it down step by step. So here's the plan. We'll start with the very nature of charge itself. Then we'll get into the law of electric force, figure out how to visualize these invisible forces, check out something called a dipole, learn a really cool physicist shortcut, and then wrap it all up with the key formulas you'll want to remember. Okay, first things first. Before we can even begin to talk about fields or forces, we have to meet the star of the show, the electric charge. This is it. This is the fundamental property of matter that's behind pretty much all electric and magnetic stuff. So in the universe, charge basically comes in two flavors. You've got positive and you've got negative. Think of protons as being positive and electrons as negative. And they live by one super simple, unbreakable rule. Opposites attract and likes repel. That's it. That one little rule is the foundation for everything we're about to talk about. Now, all electric charges follow three basic rules, no exceptions. First up is additivity. This one's easy. They just add up like regular numbers. So a +2 charge and a -1 charge gives you a total of +1. Simple. Second is conservation. This means you can't just create or destroy charge out of thin air. You can only move it around, like from your hair to the balloon. The total amount of charge in a system always stays the same. And that brings us to the third rule, quantization. And honestly, this one's a game changer. It means that charge comes in these tiny, discrete packets. It's kind of like money, right? You can have $1 or $2 or $100, but you can't have half a dollar. I mean, not as a single coin. The smallest piece of charge is called the elementary charge. We label it E. And every single charge you'll ever find in the universe is just a whole number of those little guys. All right, so we've got the basic rule down. Opposites attract, likes repel. But by how much? Just how strong is that push or pull? To figure that out, we need a rule book, a mathematical one. And here it is. This is Coulomb's law. Now, I know formulas like this can look a little intimidating at first glance, but don't worry. All this really is a precise recipe. It's a recipe for calculating the exact force between any two charges. Let's break down what it's telling us. Okay, so here are the two big takeaways. First, the bigger the charges, the stronger the force. That's what proportional to the product means. Makes sense, right? But the second part is even more interesting. The force gets weaker as the charges get farther apart, and it gets weaker fast. That's the inversely proportional to the square of the distance bit. So if you double the distance, the force doesn't just get cut in half. It drops all the way down to 1/4 of its original strength. That's a huge deal. Let's plug in some actual numbers to see how this works. Imagine we have a positive charge and a negative charge. They're pretty small, and we place them 5 centimeters apart. When we run all those numbers through the formula, we get a force of -21.6 newtons. Now, that negative sign is super important. In physics, when the force is negative, it means it's an attractive force. It's the math literally telling us what we already knew intuitively. These opposite charges are pulling on each other. Okay, that's great for two charges. But what about when you have a whole bunch of them? What happens then? Well, that's where something called the superposition principle comes in. It sounds really fancy, but the idea is actually super simple. Imagine a few people are all pulling on a box from different directions. The way the box moves is just the combined effect of all those individual pulls, right? It's the exact same idea with charges. To find the total force on any one charge, you just calculate the force from every other charge individually, and then add them all up, making sure to account for the direction of each pull. That's what we call a vector sum. So this brings up a really deep question. How does a charge way over here know that another charge is over there? How do they push or pull on each other across empty space? The answer is one of the most important concepts in all of physics, the electric field. You can think of it as an invisible sphere of influence that every single charge generates around itself. The best way to think about an electric field is like a force map of space. For any single point in space, the field tells you exactly two things. If you were to drop a positive charge right there, what direction would it be pushed and how hard would it be pushed?
It's a way of describing the charge's influence on the space itself, waiting for another charge to come along and feel it.
But how do you see something that's invisible? Well, physicists came up with a clever tool: electric field lines. Think of them like the lines on a weather map, but for electric forces. They have a few simple rules. They always start on positive charges and end on negative ones. The closer the lines are together, the stronger the field is in that area. And they can never, ever cross. Why? Because at any single point in space, the force can only point in one single direction.
Okay, so we've been talking a lot about individual charges, but in the real world, especially in chemistry and biology, they often hang out in pairs. And one of the most important pairs you'll ever see is the electric dipole. So what is a dipole? It's really just a pair of equal and opposite charges separated by a little distance. The classic example is a water molecule. It has a slightly positive side and a slightly negative side, which makes it a natural dipole. And we have a way to measure its strength and direction. We call it the dipole moment. It's basically an arrow that points from the negative end to the positive end. Now, here's where it gets cool. What happens if you take this dipole and stick it inside a bigger, uniform electric field? Well, the field is going to pull on the positive end and push on the negative end. This creates a twisting force, a torque, that tries to spin the dipole and line it up perfectly with the field. It's almost exactly like how a compass needle tries to align itself with the Earth's magnetic field. All right, so using Coulomb's law to calculate electric fields can get, well, it can get really messy, really fast, especially if you have a lot of charges. But thankfully, for situations with a lot of symmetry, physicists have this incredibly powerful and honestly beautiful shortcut. It's called Gauss's law. So here's the big idea behind Gauss's law, in plain English. Imagine you can draw an imaginary bubble, any shape you want, around a group of charges. Gauss's law says that the total amount of electric field flowing out of the surface of that bubble is directly proportional to the total amount of charge you trapped inside. It's a really profound statement. The stuff on the inside determines the flow on the outside. And that's why it's such an amazing shortcut. If you tried to find the electric field of, say, a perfectly charged sphere using Coulomb's law, you'd be stuck doing some truly gnarly calculus. But with Gauss's law, you just draw a nice, symmetrical bubble around the sphere, and the law basically lets you solve the whole thing with just a bit of algebra. The trick is always picking the right shape for your imaginary bubble. Wow. Okay, we have covered a lot of ground. So let's just pause for a second, take a breath, and put together a little toolkit of all the core ideas and formulas we've just talked about. All right, here are the big ones. We've got quantization, the idea that charge comes in packets. There's Coulomb's law, our tool for calculating the force between two charges. We have the definition of the electric field itself, which maps that force in space. We've got the dipole moment to measure those little charge pairs. And of course, the incredibly powerful Gauss's law, which connects the field flux to the charge inside. You know, to really get good at physics, you have to learn to speak the language. And this table right here is basically your dictionary. It shows you the key ideas, the symbols we use for them, and the units we measure them in. Getting comfortable with this is absolutely essential to really understanding how all these pieces fit together. And that leaves us with one last really big question to chew on. We've just spent all this time learning that like charges repel each other. So why doesn't the nucleus of an atom fly apart? I mean, it's packed full of positive protons all crammed together. According to everything we've just learned, it should instantly explode with incredible force. The fact that it doesn't tells us there must be another force at play, something even stronger than electricity. But that is a story for another time. Thanks for joining me.